Hi, this is Louis Avoldi presenting my final project, Cascading with Java for Harvard Extension School's E-63 Big Data Analytics. Cascading for Java is an open source data processing abstraction framework that sits on top of Hadoop, masking the complexity of MapReduce. It's built for the enterprise to work on large, complex data processing flows. It's geared to improve developer productivity by making use of reusable patterns and simplifies operations by producing one single deployable jar file. Various partners and distributions such as SpringSource, Amazon AWS, Hortonworks, Microsoft Azure, and companies such as Twitter, Etsy, Airbnb, and Williams-Sonoma have published large use cases using cascading. All cascading applications begin with a source and end with a sync tap. Data flows through streams as tuples through filters, functions, operations, and aggregators. Here's an example of the word count program. Here we have our source and our sync. Here's another source. There's a join. There's some operations. Let me show you some examples in source. First, I'll go over the source tap, an example of pipes, functions, and filter, joins, sync tap, and connecting the pipes together. Remember, source taps are for reading data onto pipes. In this example, we're reading a text-delimited file with the following fields. The fields right here are defined as tract ID and year. This specific file has a column header and it is comma delimited. And the file name is track year dictionary path, which is nothing more than a file name. The result of that is stored into this tab called Track Year Lookup tab. Pipes carry a stream of tuples. Later on, when we connect the pipes, we'll be connecting a source tab to put data onto our pipe and then feed data off our pipe into a sync tab. To define a pipe, it's pretty straightforward. Call the new pipe constructor and feed it a pipe name. That's it. The next two lines demonstrate how to implement a custom function and a custom filter across each tuple of the supplied pipe. So as each tuple passes through the pipe, the custom function or the custom filter will be invoked. In many cases, we will have to join one or more pipes into one single pipe. To do that, we can make use of the cogroup or the hash join operations. The only difference between these two operations is hash join operates in memory, so be careful when you're operating on large data sets. In this example, I'm using cogroup to join two pipes, track year lookup pipe and lyrics pipe. On the join field, track ID from the lookup pipe here, and also the same field name, the lyrics pipe. Now in this scenario, since cogroup just concatenates the fields of the two pipes together into the output stream, we would have an overlap of field name track ID. So in this scenario, I need to define the output fields, renaming the join field names. And that's what this track ID 2 is and track ID 1 is. Here I'm defining a sync tab. As you can see, it's very straightforward. Simply call the constructor on the default Hadoop file system and feeding a text line writer that will write tuples straight to the results file. And finally, we connect our pipes. Here we're defining a flow definition which couples our source taps to our pipes and finally our pipes to our sync taps. Once that flow definition is defined, we complete the job, which executes the flow. Installation and use of cascading is simple. Simply include the following dependencies into your project, package the application dependencies into a single jar file, and deploy and execute the jar on your favorite Hadoop cluster. Here's the use case I'll be implementing. Using the Million Song Dataset along with the MusiXmatch Dataset, I'll be creating a series of word clouds visualizing the top used words within the lyrics by the decade. Let's talk about datasets. First off, I'd use the Million Song Dataset, which is a freely available collection of audio features and metadata for 1 million contemporary popular music tracks. I use the summary file version, which is in HD5 format. This is a unique format, ideal for extremely large, complex collections with lots of metadata. In order to open the HD5 and convert it to a CSV, I downloaded and used the HDF View application. Here you can see the resulting file that I had created, essentially two columns with the track ID and the track year. We'll use this file in conjunction with the other files. The MusiXmatch Dataset is the official lyrics collection of the Million Song Dataset. It has 237,701 tracks with lyrics. The lyrics come in a bag of words format. What this means is that each track is described as a word counts for the dictionary of the top 5,000 words across the set. As an example, here's the data file. Here's the bag of worms that I was referring to. This is the list of 5,000 words. It's held as a single record in the data file at the top. Each word is associated with an index, starting with 1, 2, 3, 4, and onward. Following the bag of words are the track records with the lyrics. The format for those are the track ID, the song ID, and then the frequencies in this format. What this means is word with index 1 occurred 6 times, word with index 2 occurred 4 times, and so on. To prepare this data set for my cascading application, I simply removed the comments, pulled out the bag of words into its own file, and the remaining lyrics and frequency counts into its own file. So it resulted in two separate files, a word dictionary file and a lyrics file. The final input data set that I'm working with is a data set of stop words from ranks NL. This dataset contains words that I would like to filter out from my lyrics. To build the dataset, I combined common stop words from the top 8 languages that may occur within the dataset, totaling 1,066 stop words. Here is a high-level view of the steps needed to implement my use case. I'll be deploying my lyric machine cascading application to AWS, which will produce results in S3 buckets. From there, I'll do some manual processing and finally produce my word clouds. Now it's time for a demo. In this demo, I will review the project and source code in my IDE. I will execute a manual build. I will review AWS's deploy script that I've constructed. In that script, I use CLI commands to build up an AWS cluster. Also, I will talk about how I used S3 buckets. I'll also verify that the project is building in AWS and verify that output results are indeed produced. Okay, so here we are inside my Eclipse IDE. This is my project layout on the left. My package structure is very simple. At my root, I have a driver class, which is essentially the entire application. Over here I have a filter package which has one filter. This filter simply validates the year. And then over here I have a function package which has two functions. And this is a function that converts the year to a decade. And this one is one that transposes the lyrics. And we'll look into that a little deeper here in a minute. Down here is my POM file. This is my Maven build file. And I'll just walk through this real briefly. There's the repository where the cascading jar files live. There's my dependencies. Very simple. Over here I'm using 3 plugins. The first plugin is a compiler plugin using JDK 1.7. Second plugin is a dependency plugin. And what the function of this plugin is to actually copy all the dependencies of the project, which is my Maven dependencies, and package them using this plugin into a jar file so that the Cascade application along with all the dependencies are packaged and packed up into one single complete jar file. So there's a couple of quick things I want to point out about the source if you're going to build and compile this on your local computer. You can actually run this whole job, when I say the whole job, against the reduced set of data simply by using the local scheme. So this is just simply adjusting your imports to use the local scheme versus the Hadoop scheme, and in changing your taps to use the file tap instead of the HFS tap. And then the last thing is use the local flow connector instead of the Hadoop. So making these simple changes here will let you execute the job on a limited data set on your local computer. Um, One other thing I wanted to point out was the filters and the functions. So let's look at the convert to decade function. The functions extend uh, the base operation, and here you can see I'm implementing a function. And what that does is requires me to pass the number of input arguments to the superclass, and then I'm going to define uh, what is going to be returned back to the stream. So this is important, and this caught me up. So what this is saying is that after this function runs, I'm going to put this field and this field back onto the stream. Now, the other method that you do need to implement is the operate method, and this is where the really the function takes place, and it's simple. You're getting the arguments right here. You can see I'm getting the first argument, the second argument, which is first argument is track ID, second argument is year, and then I'm simply just taking the year and I'm replacing the last character in the year with a 0 to create the decade. And then I'm taking that year and I'm building up a new tuple, and then I'm adding that tuple back to the collector. And that's a simple function. The filters aren't much different. In fact, the filters are even simpler because in this case, you're not returning tuples back or tuples back to the stream. You're simply just removing tuples based on the criteria of the implemented is remove method. Okay, and just to show you that the project does indeed build, over here in my command prompt, I'll just type a Maven clean package. And there we can see all the project dependencies being packaged into a single jar. And just to show you the contents of my target directory, there we can see my lyrics machine.jar. And this is the jar file that we will deploy out to AWS. Now let's take a look at the script I put together for taking care of some routine repetitive tasks. Going through the script, you can see I'm supplying the arguments for my application, which includes my input data and then output paths. Over here, I'm setting where my application lives. Here's the name of my application, my jar. Here I'm changing directory to that location, doing a Maven clean package to do a clean build. Here I'm clearing out the output bucket from in S3. Over here I'm copying the created jar file from my Maven package command out to S3, and then I'm creating and executing an EMR cluster, feeding it various parameters and switches. You can see I'm using the large instance type. That's a 3-node cluster. And then over here, a couple important things is one is to auto terminate. That way you don't accidentally leave your cluster running and to incur excessive charges. And another thing here is where I'm actually feeding the path to where my jar was deployed in S3. Okay, so let's get out of this script and we'll go ahead and execute the EMR script. And here you go, it's kicking off a Maven build. You see the build was successful. There it's clearing out the contents of my S3 output directory. At this point, the script is uploading my cascading jar file that was just built via Maven. Here you can see my completed built cascading jar is now being uploaded to my S3 bucket. And the file is uploaded, and now we can see the cluster was built and the cluster ID here is specified right here. Now let's go ahead and check out. Great, so now my CLI job created the cluster and uploaded my jar, and over here you can see the actual cluster is running. It's in a starting status. There's the cluster ID I had mentioned that was outputted from my CLI script. Drilling into the cluster, you can see my step, my Lyrics machine step is running. We can click into that, and we can see the actual location of the jar, which is in one of my S3 buckets that the shell script uploaded via CLI. And then there's my jar files arguments, and you can see again referencing S3 buckets, and these are actually the input data sets, and at the same time we're also referencing where we want the output to go. And there's also a couple of other outputs for the different tabs, and I really use that for debugging purposes. So looking at the S3 buckets, you can see right now we have our output is just starting to populate. Not done yet, so we'll wait for that to complete. There's our log bucket, and you can see these are a lot of some of the previous jobs I ran before. Going back to the root, here's where the jar file for the Lyrics machine, the output of my Maven job, was uploaded to S3, and we saw that referenced in the job step that was created. Here's where my data files were uploaded, and you can see I actually have some short ones that I was using for debugging. This job's actually running with the full data set. And let's go back and check on our instance. We'll refresh the status here. We can see it's still running, so we'll give it a few more minutes. Okay, here we can see the job's completed, and there is some output to look at. So next thing we'll do is switch back to the shell, and we'll download the results of this output back to my local file system on my Windows computer. So back at my shell, I'm going to go ahead and download the contents of my S3 output bucket to this output directory. Okay. Looking at the contents of the output directory, and next thing is I'm just going to concatenate all of those into one single file. And we can take a quick peek at, let's actually just look at the head of output.txt. And there's the contents. So using the Wordle site, I uploaded the data from each decade and produced one of these word cloud images. Here you can see this is the word cloud from the words from the decade of 1920. Notice things like, the word mama, baby, Lord's pretty big. But going through the decades, you can see some of the words are shrinking in terms of frequency, while some are getting larger as the frequency goes up. In 1940, 1950, you can see love is getting bigger there. 60, 70, 80, 1990, 2000, 2010, and that's the final one there. And this concludes my presentation on cascading for Java. Thanks for watching.